Polyprotic acid is an acid that has multiple acidic hydrogens. So that's a diprotic acid. That's a triprotic acid. That's a diprotic acid. Here's the great news for you. Okay. Number one, if we talk about diprotic acids, the first thing you need to understand is that the hydrogens come off independently in multiple steps. So, for example, if I take H2CO3, it does not do this. You don't give them both off at the same time. What actually happens is this: it donates a hydrogen, one hydrogen, and you get the bicarbonate ion. And then this still has an acidic hydrogen on it. How do I know it's acidic? Acidic hydrogens are always written at the beginning of formulas. Okay, if it wasn't acidic, then they would have written HCHO3 or something like that. Like they wouldn't have, but because that's in the front, we know that it's an acidic hydrogen. So now this guy can lose another hydrogen. So now in a second step, the second hydrogen would pop off. Let's talk about some of these things. The first hydrogen coming off is always more acidic than the second one. So if we call this Ka1 and Ka2, the first acid dissociation constant, Ka1, is always much, much greater than the second acid dissociation constant. And this is wonderful news because unless you're an analytical chemist, okay, the amount that the second hydrogen comes off on a diprotic acid can usually be just completely disregarded. Like it's such a small amount, it's not even funny. Now, there is one exception. The one exception, and you're not going to have to do the math for it, but I want you to understand this. The one exception is sulfuric acid. So hopefully you're working on memorizing those 6 strong acids. Hopefully you saw how important that was after yesterday when we talked about the acid-base properties of salts, right? Because you got to know the 6 strong acids to know their conjugate bases to be able to determine what kind of salt you got. Okay. Sulfuric acid is special. That is one where you would, even if you're not an analytical chemist, that's one where you would have to worry about that second hydrogen coming off. Here's why, folks. Okay. Since sulfuric acid is a strong acid, the first hydrogen that comes off is actually the only one that's strong. So we use a single-headed arrow for that because the first hydrogen fully dissociates and you get H plus and then the bisulfate ion. And then this guy, okay, is a weak acid and it'll partially dissociate. But because this guy fully dissociated and you have a whole lot of this, in fact, it's all been turned into this, there's so much of this that the amount of hydrogens this generates is not negligible. So you do have to worry about it, okay? You're not going to have to do the math for that, but I just want you to know that sulfuric acid is special, and you actually get a higher H plus ion concentration than the H2SO4 concentration. For example, say it was 2 molar sulfuric acid, the amount of total H plus in there is actually a little greater than 2 molar because you get 2 molar H plus from this, and then this dissociates, you get a little more. So it's a special acid, right? Okay, also known as battery acid. So there we go. That's our polyprotic acids. We'll look at titration curve for polyprotic acid later tonight once we cover pH titration curves. Here, I just wanted to prove to you that the second, for unless you're sulfuric acid, the second deprotonation event produces essentially a negligible amount of H plus. And before we even do that, let me draw your attention to the Ka value. So here we have ascorbic acid. That's actually vitamin C. Okay, so vitamin C is a diprotic organic acid. The first hydrogen that comes off, that has a Ka value of 8 times 10 to the negative 5th. And the second one that comes off has a Ka value of 1.6 times 10 to the negative 12. So if you had a 0.1 molar vitamin C solution, the amount of H plus from the first dissociation is 0.0028 moles per liter. And then this second guy deprotonating, the conjugate base from the first reaction, that one giving off its other hydrogen, that only gives you 1.6 times 10 to the negative 12 moles per liter more hydrogen. It's negligible, right? I mean, 0.0028 plus 0.000000000016 that second H plus, it doesn't matter, right? Unless you have like 50 sig figs, it's not gonna affect anything. So